All right, we are ready to develop our test for whether F is a conservative vector field or not. I'm going to first of all work with it in 2 space. There's a similar test for vector fields in 3 space. I'm going to actually start by just saying something that is true if F is conservative. Okay. So if F is conservative, then I know that there's a potential function. So with f of xy equaling its potential function, then I would know that f was actually the partial of f with respect to x, comma, the partial of f with respect to y, because it would be the gradient of that potential function f. But I've already given names to those things, so that would mean that p of xy was the partial of f with respect to x, and q of xy was the partial of f with respect to y. Okay. All right, so that's if it's conservative. If it's not conservative, there's no function f that would make this true. So I can't just write this unless I know that my vector field is conservative. But now let's suppose that in addition to being conservative, these component functions have continuous first partials. Okay. So they already are the first partials of f. So if I take the partials of a conservative vector field, I'm actually taking the second partials of the potential function f. And if those are continuous, I know something about them. I know that the mixed partials are equal. Okay. So if I take the partial of p with respect to y, because I'm saying if it's conservative, p is already the partial with respect to x. So to get to a mixed partial, I would have to take the partial with respect to the other variable. So this would be the partial with respect to y of the partial of f with respect to x. Okay. And if I took the partial of q with respect to x, because we're saying if it's conservative, q is already the partial with respect to y, so this would be taking the partial with respect to x of the partial of f with respect to y. These would be the 2 mixed partials. So if f is conservative and if its component functions have continuous first partials, these guys will be equal. Okay. So if p and q have continuous first partials, and those first partials are actually the second partials of f, and f is conservative, then the partial of p with respect to y will equal the partial of q with respect to x. Okay. So that's something that we can see is true. I'm just going to call that equation star. Okay. Now, good question to ask is, does it work the other way? If this equation is true, does that mean that f is conservative? And the answer is almost. If this equation is true on a simply connected region, my vector field will be conservative on that region. Okay. So let's write that out. So if f of xy equals p of xy, q of xy, on D, and D is simply connected, and P and Q, the component functions of f, have continuous first partials. So if all of these things are satisfied, so I need one thing to be true for the component functions, they have to have continuous first partials. I need one thing to be true for my region. It has to be simply connected. Okay. Then, if the partial of p with respect to y is equal to the partial of q with respect to x, then f is conservative on that region D. Okay, excellent. That's actually going to be a fairly quick test. I will warn you, this is what students always forget. They remember to do this test, they forget to just observe. It's usually just an observation. Hey, I'm working on a simply connected region. Often that simply connected region will be the domain of your vector field, and often that's going to be all of 2 space. So, let's just try an example. Let's let f of xy equal, let's go with y e to the xy, x e to the xy. So I'm going to call this function p and this function q, just following the notation that the book generally uses. Okay. I'm going to just point out that the domain of this is all of R2, which is simply connected. And then I'm going to take the partials to check. Now, be very careful. I don't yet know whether this is conservative. So, to remember what the test is, I'm thinking if this is conservative, this is already a partial with respect to x, so I would want to take a partial with respect to y. Okay. But I don't want to actually write that this is the partial of f with respect to x, because I don't know that yet. I haven't established that such a function f exists. Okay, so I can think, I'm hoping that already is, so I'm going to take the partial of p with respect to y, okay, which means it looks like I'm using product rule. Okay, so the partial of y with respect to y is just 1 times e to the xy plus y times the partial of e to the xy, which would be e to the xy. Chain rule, the partial derivative of xy with respect to y would just be x. So that's going to give me e to the xy plus xy e to the xy. Okay, then I can take a look at del q, del x. If this one was with respect to y, this one's going to be with respect to x. Again, while I'm not going to say until I've established it that this is the partial of f with respect to y, because I don't know whether such a function f exists or not, I can take a look at this and say, if it's conservative, that's already a partial with respect to y. If I want to get to a mixed partial, I need to take the partial with respect to x. And looks like, again, that's going to be a product rule. Partial of x with respect to x is just 1 times e to the xy plus x times the partial of e to the xy, which would be e to the xy. Chain rule, partial of xy with respect to x is just y. So I'm getting e to the xy plus xy e to the xy. Oh my goodness, they're the same. So I can say the partial of p with respect to y equals the partial of q with respect to x on R2, which is simply connected. F is conservative, and that would be true on all of R2. So it's conservative everywhere. I know now that there exists a potential function for f. All right. In the next video, we'll take a look at how we would actually go about finding a potential function after we've verified that we have a conservative vector field. Okay. And we will come back at some point and talk about why this simply connected is an important thing. Okay, we'll get there. It's just not coming up yet, right away.